The lecture will develop along projects, along very different projects, starting with very old ones, passing through applied projects that partially were done in our practice, so the practice of architecture, transiting towards research project, more and more speculative one, and ending with utopia. The concept that ties together all this project and gives the name to the lecture is digital materiality, which is a term we created by taking two concepts, the concept of the digital and the concept of the material, which are familiar to everybody, and by combining them in a very direct way. And this expresses, and we did this 10 years ago, this expresses the search for something in architecture that happens when these two realities meet, that exists at the interface between those two things. And it's also a political statement saying that for us, the digital and the material that for a long time still in some scenes, probably for you, I guess, 3/4 of you is digital native, maybe make less sense, but for my generation, where dramatic, these two worlds were colliding one with the other. And in architecture, this was very strong, this collision. It was a generational conflict, it was an ideological conflict, and the point of departure of our architecture is by dissolving this conflict. You know, we say there is no reason for a antagonism between the digital and material, but they belong together because they both are architecture. Now, we started, Matthias and I, to deal with the digital long time ago, before studying architecture. Exactly mid-80s, when we were teenagers, we belonged to this, it's not a generation, it was just a few years that was teenager when these machines that were already computers, but not gaming computers, but cheap enough to be owned by kids, but didn't have a graphical user interface. This came a few years later. It was sort of a very thin time window. This machine were called Commodore 64, for example, and kids played with these things. And the game was programming, among other things, because there was nothing else this machine could do. You know, it's hard to imagine, you know, but this was the attraction to this machine. The result was that we learned to program, I mean, very poorly, but we learned to program not as a professional activity, but as a playful activity. And we internalized these concepts. We found really thinking about it, and then 5 years later, when beginning of the 90s, when we studied architecture, and beginning of the 90s, the first half of the 90s was an exciting time because it was the moment when the internet was born. And at university, at the big university, you had access to internet. And internet was nothing more than a few hundred pages, you know, and very slow browsers. Most of it was waiting. But this and the diffusion of mobile phone and all these things were sort of anticipating radical change in the way we live, in the way we think, in the way we conceive everything, us in the city, the relationship between people and so on. And this was still to come, but was in the air. And at the same time, CAD, so computer-aided design, was also coming up. These were expensive machines that only university had, a few offices had them. Architects said, we'll never use this, why should we? 95, these were statements you could hear. 10 years later, everybody had them, for other reasons, not because we love them, but because we need to use them. And in this context, we learned architecture in a very traditional way, by drawing it, not with computers. We were educated to think about space, about material, about construction. And the dilemma for us was that these two worlds, what we learned before and what we did were very similar. So the intellectual activity when you program is very similar to the intellectual activity when you design. You bring things in an order, you create hierarchies, you create a synthesis, you decide, and so on. But there was no connection. Nobody understood beyond this, other than this similarity, what could be the connection. Because back then it was all about digitizing the world. We digitized our profession. In 10 years, we went from drawing on paper to drawing on computer. It looks like the same thing, but it's not. If you draw on paper, you create information, that is analog and that you can interpret by looking at it. If you draw the same line on a computer, you create coordinates, points, and points are data. And this data can be duplicated, manipulated, transferred, printed out to be interpreted again, and this is the point where we started to be interested again in this combination, can be used by a machine to execute physical operations in space. So the point for us was that after 20 years of digitalization of reality, we wanted as architects to look into the reverse direction, into the future. So if we have all this data, and we have changed our profession, but we are not producing more interesting stuff. Maybe we can produce more complex designs, but we have no idea how to realize them, So the added value is pretty poor. And all these colleagues that in the 90s were saying we'll never have a computer in our office had one, not because they liked it, but because they were obliged by economical conditions. Because the machine makes you productive. But being productive is not an advantage to architecture. Maybe it's a strategy to survive, as an architect, but it's not. And we were looking for this shift. So going from data to material again. These are the concepts that are underlying to all the projects I will show you. To make an entry into projects, I'll like to start with very old. It's rather an experiment than a project. It's not research because it's conceived outside of academia. It's something at the interface between an art piece, a provocation, or an installation, maybe. It was called M-Table. It was about creating a piece of furniture, a material furniture, in this case a table, on a mobile phone. And this was the first smartphone. This was a Nokia in 2002, 2003. The term smartphone didn't exist back then, but basically it had all the characteristics. And it had one nice characteristic that Nokia didn't even know about. They had the technical feature that you could write applications, so apps, but the term app didn't exist, But you could write application and then download them to your phone, install them, and run them. So we said, why not use, for this experiment, why not use a mobile phone instead of a computer? Would have been simpler to allow a layman, so a client potentially, a user, to design something. You know, this decision is very important because this smartphone was not perceived as a computer, but was perceived as a phone. You know, so an accessoire, a gadget, something you have in your pocket. So suddenly on this thing you can design a table. Now, how did it work? Here you see an old pixel movie. You could set points on a surface, and by pushing on the joystick, you could apply a force on these points. This force would deform the surface, and the deformation, when its magnitude is high enough to intersect with the other surface of the table, creates a hole. And the touchscreen didn't exist. You had a joystick. What was even nicer, because you were pushing physically, you know, and then deforming this thing. At the end, you have seen in the video, you could also, of course, choose dimensions, color, material, all these usual things of customization. But the radical thing that you were allowed to intervene on form, you know, and to intervene on form on a level that is ambiguous, you know, because to intervene on the size of a table is one thing. To decide if a table should have holes, it's a completely different story, you know, because holes on a table under circumstances make little sense. So you are undermining the function itself of the object you are creating. But I will get back to this later. Now, technically speaking, what happened, in the end, you were sending your design, and what you were actually sending without seeing it was this information. These are the parameters. It's extremely straightforward, simple, human readable, authorship, color, dimensions, and XY position of these points, and the magnitude applied. And this information, if you know the rules of the game, so if you have the algorithms of the algorithm of the design that I've shown you before, allows you to geometrically construct such a surface. You know, it's a doubly curved surface of an extreme complexity, but mathematically defined in a rather simple way only by these parameters. And by post-processing this information, you can send commands to a machine, a simple CNC router that at the time was already standard in industry. And then you could transfer this information into walnut wood, so a very expensive and high quality and high definition and hard material. And then create objects that look like this or like this, that are at the same time very elegant, unique, and as I said, also problematic, because they address this question of authorship, of design, you know, responsibility. So the question here is if you connect directly this device, you know, with a minimal interface size, so very low resolution, you don't see anything, you know. We had a 3D animation, but you couldn't really judge if what you're doing is good or bad. And then just by sending, and of course paying a lot of money in between, you know, this limited our series to 10 pieces, you end up with this. So these two worlds are connected in the most direct way possible. Now, of course, this doesn't make sense, but for us as an investigation on the consequences of this new world, and not just in the technical possibilities or let's say potentials and so on, but also in the very problematic issues, you know. It was the perfect setting. But you see here, it's a collection of just rendered. We had hundreds of them. You know, each one of these has somebody out there that spent something in between 3 seconds and hours, you know, thinking about the possibility of creating a piece of matter and eventually ordering it. Now, the question is, who is the author here? You know, of course, these people put authorship into it, but they were acting in guidelines that we set, you know. And the important message for us that this project still conveys, and this is the reason why I still like to show it, it's still actual for us, is that we as designers, we should not be afraid of parametric design, because parametric design is the opposite from everything goes, you know, because parametric design just shifts the act of designing to another level, you know, and it's tough to let go because we have been educated to understand, think of us as the profession that gives form to things. So we are, you know, and here to say, okay, we don't care about form, and we don't even care about function. Let's decide somebody else if wants hole. I mean, it's his table, you know. If he has a hole, he will live with it, you know. This was pure provocation, but what this image shows is the positive message, you know. These objects all look the same. They're all different. Some of them are super beautiful, elegant, others are extremely ugly, you know, but they all look the same. So they have an authorship, you know, that belongs to the designer, you know, and the designer is the person or the collective or whatever who conceived the rules of the game. And in this case, conceiving the rule of the game was literally to write a piece of software, an app, that back then wasn't called app, you know. Nokia didn't even know that they had it. This is tragic, you know. Nokia was sent out of market by Apple with apps. They had it in 2002, but the management and the marketing didn't know about it, you know. Okay, this is a side issue. Second project, very different. It's a bit younger. It's not an experiment. It's a private house. It's a piece of architecture, but has a close relationship to this last project because it's very much about parametric design, and I use this project to explain what parametric design means to us. And also that parametric design is a very simple thing, and for architects a very familiar thing. It really belongs to our thinking and our culture. It's a private house. It's here in a small village nearby Zurich. Very nice setting. Very, very difficult because it's protected environment. You can do not much. It has a lake on the left, and here I show you the plan. So the house is this one. It has a strange geometry. Now, this strange geometry, of course, you will assume has something to do with the context. This is the way we design, you know. We never rarely have tabula rasa, and normally we don't like it because we need friction and constraints. But I need to tell you why it has this shape. So basically it's a rectangle with 2 cuts. The first cut is the consequence of the fact that the new house is, so the plot is owned by the client is living in this house on the right. So it's a classical situation. Somebody builds a new house in its own garden, you know, in its view onto the lake. So what you want to do, you want to put it in a way to preserve the view from the old house, a classical setting, you know. And now in order to do this, you cut. There is not much you could do, and what you could do is to cut more or less, you know. And if you cut more, the new house gets smaller, and the view gets bigger, or you cut less, and yeah, it's simple, you know. This is relationships, and it all turns around one angle. So you can describe this relationship in one angle. And the second cut has a very similar reason. You want to park your car on the back of the house. Again, it's logic. The entry is very difficult, so you need a radius, and the only way to fit the car on the back of the house is to make a second cut, and you end up with this thing. Here, it's more deterministic, you know, because you can estimate what car you will have and what the radius is and so on. Yeah. Now, the question here is, this is fully parametric. I can write a program describing this, you know, but I don't do it. And nobody would do it, you know. Why? Because it doesn't make any sense. Because it's the way we design. So we understand the problem, maybe we invent the problem, and then we iterate through this problem until we discard the problem and find a new one, or find a solution that satisfies us and the client and the authorities and so on and so forth. And this problem can be iterated on a piece of paper. I don't even need a piece of paper. I do it in while sleeping, you know, until I find a good solution. Okay, so parametric design, no programming, no computer needed. Now, very quick, the house is not the topic here, but give you an understanding, this is the floor plan, ground floor. It has a core with stairs and services, kitchen and so on. A swimming pool on the back. The section looks like this. This core goes into the second floor and carries a pitch roof that is cantilevering on 4 sides. This is the facade. What is particular of this second level is that it has no window, but it has a ribbon, a glass ribbon, that is following the line of the roof all around. So very simple. Now the problem here was that the building regulation didn't allow glass as a material. So you could do windows, but vertical 1 square meter. We tried a lot, but didn't really fit, you know. And we needed windows, of course. So the trick was, and this is a pretty common trick, we did it before on other objects, was to veil the whole house with an additional layer of, and you see them here, timber slats that are perpendicular to the facade, have a spacing of about 20 centimeter that on a phenomenological way you don't see anymore if you're close to them, because you focus on the background, you know, on the view, and so you internalize this. This works very well. While from the outside, this house looks windowless, you know, completely closed and homogeneous. Now, if we look here on the right, we see that this veil, you know, second layer, is not homogeneous as it looks from far away, but it's somehow treated, it's worked. And if I show you these drawings, I can explain you how this works. Here I have the front view, and in the side view of such a slat, you see that it has been milled out, slimmed out at certain heights. And if you look at the plan view here, you see also that these cuts, this thing, are can be perpendicular, but can also be inclined. And this, you can imagine, enriches this screen with the possibility to control perception. So by slimming out, I can, at a certain point, I can create a sort of a window, a virtual window, where my field of view is amplified. And with the inclination, I can control which side, is prioritized. So it's sort of a viewing machine, a very discrete viewing machine that allows you to instrumentalize classical architectural categories, whether that are about view, that are about privacy, neighbors, that are about sun shading, south, north, etc., in a situation that otherwise is very indifferent, to the environment, because this ribbon just goes around the house in a very formal way. Okay, this is the problem statement. Now, what is the consequence of this decision? Again, it's very simple. It's parametric. I say I have a slat, has a height, then I can define a height, and I can say, okay, on 1 meter, I cut, I slim it out by 5 centimeters, for example. So this is all variable. The problem is that I have 315 of them, and it's a small house, And because of the fact that the roof is pitched and so on, and the window is not horizontal but following, you won't find 2 slats that are identical, not even similar, So suddenly this problem that in the same house at the beginning was described as two angles, here pops up again, but now you can forget about doing this without a computer. You cannot design it. You can create a rule, but then you're blind. Then you can say, okay, nice, and now, should I start modeling or drawing each slat? If we recall us that designing is an iterative process, you cannot just design it right. You do something, look at it, redo it, look at it, redo it, and then eventually you will like it, Here, 315 slats. Calculate the time to model one, One iteration is a few days, No way, doesn't make any sense. And the second problem is, even if you would have so many slaves that do all these things, how do you produce it? If you go to a contractor with 315 drawing, he will do it, but it will cost so much money, that it doesn't make any sense anymore. So the solution there is reduce a bit the volume, to look for a machine like this. Again, available in industry, very simple machine. It's used every day to trim linear elements. It's digitally driven, and by chance it has also this axis, Now this machine does, if you feed this machine the right data, just does these 315 parts for free. For free, because the machine, each part, if I would say I want 315 slats, 20 centimeter high, what does it do? Takes 315 slats and puts them on this machine. But it runs 315 times the same program, Now what we do is we run 315 times a different program. It doesn't cost more, it takes the same amount of time. The machine is not interested in what movement it does, it's just the machining time that you pay. Okay. A few images on the result. They will not comment, so it's a completely closed house. Had one big opening on the pool. This is how it looks inside. It's a perception machine. Difficult to describe in images because it's something that you only understand when you move through these spaces that open and close like a veil. And now here the question is really, on the design side, what came first? The machine or the idea or the program? Because if you have such an idea, write the program, you know, make a design, and then start looking for a machine, and eventually do not find any machine, then you have a problem, you know. At the same time, I don't think that we can depart from machines. This is, as often in architecture, is simultaneous, you know. We are used to think at multiple layers. When we do the first drawing, you know, we already have a material in mind. It doesn't make much sense in this point, but step by step, this thing start to find together, you know, and to create a project. So this was introduction on architecture, digital fabrication, parametric design, and so on. Now I want to switch to the question of the machine and the human. And I move into ways away from practice. One is these projects now are developed in an academic setting. So this is 5 years later. It's 2005, 2006. As experiment, as a research, so not the research in the office, the project, but this is academic scientific research at the Polytechnical School, you know. Strange for architects who somehow happen to be there at the right moment in time. And the machine is not anymore a machine that is out there available in industry, but it's a machine that already existed, the industrial robot, but that we introduced into architectural research. So this was a creative act, you know, because we were asked, what machine would you need to do your research? And we spent a lot of time thinking about this question, and eventually found out that it was a very important question, because the decision on the machine is the point of departure. We could have chosen a laser cutter, a CNC router, but all these machines, we found out, are very much limited to what they were designed for. You know, they're super efficient, but they are limited, because if you have a laser cutter, you probably use it to cut sheets. You know, nothing against this, but it's very limited. And we said, if we buy an industrial robot that also has the advantage of being pretty cheap, because it's a mass product, you know, it's not a machine that is produced in small series, it's really a mass product, it's extremely robust, it's big, it's strong. If we buy an industrial robot and just take it from industry where it has been used for 50 years to repeat, you know, and build our consumables, you know, our cars, our appliances, and take it in our lab and give it a complete different meaning and context, and understand it or start to read it as this machine that is generic by nature. You know, it's anthropomorphic and generic. In industrial term, this means that this machine is not very efficient. You know, this machine can do almost everything, but nothing in a super efficient, perfect way. So it's very similar to us, humans. We are very versatile, you know, but it's easy to find a machine that does better and faster than we do, you know. And what seduced us on the choice of this machine is that suddenly the design is not reduced to the data you feed to the machine, but it's also extended to what the machine does in space. Because the machine, when you buy, it doesn't come with a hand or with a tool. You know, no process. It's just the possibility to move in space and reach specific positions in space in a very efficient way. Maybe efficient is the wrong word, in different way. You know, the machine doesn't have better or worse positions, or simpler or more complex. They're all the same. There is only the points it can reach, because they are in the mechanical, you know, kinematic space, and those that are outside. And this brings the discussion back to us humans. And this is the second element on this image that is by an artist, the Swiss artist Jules Spinach, that is asking, who depends on who in this partnership, because the whole rhetoric of discussions going on right now, about the end of labor, although they are very serious and justified, but the underlying rhetoric is deeply rooted in a 19th century trauma, because in the last 200 years, the machine is the follow-up of the tool. You had the tool controlled and owned by the craftsman, At a certain point, the tool gets bigger and bigger, expensive, and very specialized. So it's not owned anymore by one person, but it's owned by capital. It becomes anonymous. And for more than 200 years, the scope of the machine is, of course, to allow for mass production and so on, but one very constant consequence is to get rid of the human in the process, because the human in this process is always a cost factor, a quality problem, a risk. And we are still thinking very much in these categories, because we have been educated that this is the consequence of the investment into machines. So we and the machine are opponents, enemies. We have a very deep sort of contrast inscribed. While we think that in the post-industrial era with this sort of the machines, this equation is nonsense. It's nonsense because in a post-industrial production logic, the machine needs the human as much as the human needs the machine. And we could argue that these very sophisticated machines, and the robot here is just a placeholder, an anticipation of what is to come. This machine needs us, our intuition, needs our control, the design, and so on, as a partner. You could argue that without any second thought of one being romantic or whatever, or naive, that this sort of machine is much closer to the tool of the craftsman, than to the big specialized machine of the industrialist that we still know and use. Okay. This is the theory, but I wanted to give you an example to make this extremely clear how this relationship is conceived and thought with a building process that we used as a proof of concept in the very early days. We bought a robot and then we did this project in order to understand what we were doing actually. So we started to build brick walls. I'll get back to this later. Now I'm just interested in the fact that the human on the left is building something by hand. He's not a mason, he's experimenting. He's trying to find out what the possibilities of a bond are. So everybody, each one of us has a concept of how a bond works, We have studied bonds, historic bonds, whatever, in technology classes. Maybe we have built something with Lego, maybe we have built a real wall. But still, in order to really understand what happens, what tolerances are, how it looks, if you put them in a certain order, how much you can rotate something or can deliver, you have to experience the world. And on the right, you have a very simple computer program. Now, the blue and the red part, it's the basic structure. I don't know if you can program, but if not, I can explain it to you. These are while loops. While is a structure that controls the execution of a rule sequentially for a certain amount of times. And what this program does is to put one loop into the other loop. And the nice thing is that this exactly corresponds to what the brick wall is. Brick wall is nothing else than this nested loop. Because we have a rule, or two rules. One rule is put the next brick next to the last one. And the second rule is start again a level higher. But when we build a wall, we never think about this algorithm. And again, why? Because it's so simple to execute. To program it is stupid. Okay, and it's very intuitive because when we build the brick wall, a real brick wall, we don't think in numbers. We just put next, and at a certain point we have a wall, and nobody will take the next brick and push it into the wall. Its logic is finished, and you go back and continue. Okay. Now, the problem is, or the potential is, if we add the pink parts, the pink part is math. It's very simple, where you say, I can derive a rotation or something else from something, maybe from the stone number, or from the angle of the last one, or from the angle of the previous one, and then I can add or subtract something, or can even get more complex, doesn't matter. If I do this, suddenly what before was a very clear rule, and just two, that were simple to execute because as a human, I have eyes, and I can say next to the other is here. It's not here, it's not here, it's here, If I run this program, I end up with this list of coordinates. And again, there is no repetition. It's one coordinate, x, y, z, and the rotation in this case, around an axis that you don't have to specify in a wall because it's clear for each single brick. And this is dramatically different than this one, because nobody can execute this. Nobody wants to execute it. Again, like with the milling, this machine doesn't care if these numbers are all identical or all different. As long as they are in reach of the arm, just execute it. It doesn't complain, doesn't take longer, so it's not more expensive. And what this produces is that we can, on one hand, directly connect this very human act of designing, of understanding things, of creating things, of describing things, with this very machinic act of executing something. And now if we go back to the relationship between the human and the machine, here we understand that you cannot invert these roles. I cannot say the human does this and the machine does this. It doesn't make sense, So they don't overlap, and given the fact that they don't overlap, that each one operates in a domain that is stranger to the other, we do not compete with the machine anymore. And this is the difference between this and automation. Automation happens in the 20th century paradigm if I take the same wall that the mason does since 10,000 years, and have the machine executing it. Then I have two problems, Problem one is that they compete. That the only reason to do it machinically is to be cheaper and faster. This is consequence one. And the second consequence, that may be even more dramatic, I don't make use of the technology that I have. So it's an intellectually poor, approach to technology. And the result then is this. This was one of the first prototypes, and this was the moment when we created this concept of digital materiality. We needed something to describe what happens here. Because it's deeply physical and central. And at the same time, it has a logic and a language and speaks a language that is clearly, not drawn or by humans in a traditional way with a pencil. And it's not a repetition, you know, it's purely digital. So it's something computers are good at. And then in 2005, we knew this aesthetic, but we knew it only from graphics, for example. So we start since the 90s, you know, we started to understand these things, but always on 2 dimensions, on paper, on screen, you know. And suddenly here it becomes spatial and it's 3-dimensional. And the consequences of it were then explored in a very, very early building that was realized 1 year later, together with Andrea De Platzes and Valentin Beat, friends of us. And they had a client wanting a winery, and it was a long project. They were working on it some long time, and they were finally started the building site. And then we discussed the possibility, or Andreas saw what we were doing, and he said, listen, I want you to design the facade, you know, but you have to build it with this machine. And you have to deliver it in 4 months, you know. And he was able to convince Mr. Gantenbein to stop his building site, and they were already concreting the foundation, you know, to redesign everything, because they had a traditional brick facade, and he allowed us to design something completely new. And we had this process. Of course, we had to tune it and so on, but we knew how to do it. The problem was, what do we do with this freedom? So we have now 300 square meter of bricks. We know that we can turn them all individually. Why? What do we do? So we created a digital design environment. You know, this was again, you know, because the first idea the client had was, let's write my name on the facade. And we said, not a good idea, you know. This is not what clients want to hear, so you have to bring a good idea, you know, that fascinates them. And we did it, let me show it again. We did it this way. We thought about this building that was not designed by us, it was already designed, they were building it as a basket. And we said, let's fill this basket with spheres, you know. Not grapes, perfect spheres. And let's have 3 dimensions and scramble it a bit. And then let's look at the facades, you know. Let's look at this content, virtual content, and let's translate this visual information onto the rotation of the bricks. And this was a very important topic for us, because earlier work we have done was very, very much about the 3-dimensional structural or ornamentation, you know. In the 90s, a lot of work was done on the surface, you know. Herzog de Meuron, they were the kings in these disciplines, you know. You wrap images, you know, literal images around facades. And here we had the possibility to go 3-dimensional with this, you know, because this ornament, let's think of it for a second as an ornament, you know. So the depiction of this content on the facade, you know, is 3-dimensional. If I look at one of these spheres from 2 sides, you know, the sphere in the corner is perspectively on another place, but it's the same. So there is a consistency of information, and this fascinated us a lot. Now the next question was how to produce it. This is this process that you have already seen, but here you see a movie. The robot does just 2 things. Applies the glue, because this is very complex geometrically, and once the glue is applied, it places the element on the wall. And this is the second complex action for us humans. So thing that the machine has absolutely to do. And here you see back then this wasn't such a discussion. Now everybody talks about 3D printing. Actually, this is 3D printing, just at the scale of architecture, you know, because 3D printing is nothing else than putting the material at the right place in space directly. And the rest of the process is extremely conventional. You know, it's prefabrication, the element get placed. And I mean, of course, it was a collaboration with other architects, but it also such a last-minute collaboration that the risk had to be lowered at some point. So you see the decision to think these elements as a filling, you know, in a structure was sort of mandatory, you know, because we had no clue what the structural performance of such elements are, and it was way too late to speculate about such possibilities. Here you see other images. It's a building, you know, with a facade that in the end doesn't exist, because depending on the perspective you look at it, the light source, so the sun position, the light condition, it looks completely different, can be extremely soft, can be extremely three-dimensional and plastic. From the inside, you have the revert effect. You know, here it's not the mirroring of the light anymore on the surface, but it's the contrast, you know, that is manipulated by the rotation that is interpreted by the eye. So this was, I would say, a very beautiful but still very conservative approach to this technology. And 2 years later in Venice, we were asked to do an installation in the Swiss Pavilion, and we decided to go one step further with this technology. Now, instead of pre-producing stuff, we brought the machine. This was a necessity on one side, because to transport stuff in Venice is super expensive. So you better transport the machine than all these elements. But it was also a statement, an architectural statement. You know, you had in the 50s in Germany, or throughout Europe, but strongly in Germany, you have the Feldfabrik. It was the factory on the building site for prefabrication. And this disappeared 10 years later, because in the radius of 200 kilometers you had factories, so there was no real reason to do it. But we thought about the machine. You know, the machine is not on the building site, but it's next to it, so that the elements, very complex elements, can be produced in a close range where placement is not such a deal. So you see here, this was also part, of course, of the story. The machine is producing there. Again, the design was parametric. You know, we wanted to make use of this possibility. This is the line, we called it line of negotiation. 100 meter of brick, dividing the three spaces of the Swiss Pavilion into more subspaces for the exhibition. And we wrote a program that would, out just of this line and the definition of openings and so on, create a design following structural rules, you know, because we could not make a foundation in the pavilion. So each element has to stand and be stable on its own. So the elements that were straight got curved, and a counter curve on top, balancing it in order to give them stability. And then the rest was done by the curator, you know, because the curator is the person that until the very last moment wants to change everything, you know, because he said, I got the bigger model, you know, can you move? I said, yeah, you can. We don't care. We just want a brick wall. We want it to look like this, and you can move the line of negotiation, you know. And until the very last moment before production, you know, things were changed, because the software was at every moment in time producing this, you know, the data for the production of every single element in a fully consistent way. And this was the end result. It's just the assembly of all these elements on the right space. And here you see that the difference to the winery is that here the brick wall becomes structural. So it is informed by structural logic. It's just 8 centimeter, it's paper thin in these dimensions, you know. And there is no additional support structure needed anymore. And this is part of the beauty of this. So we're talking about the addition of parts, you know, of identical parts. Here I have a second example that is a sub-part of a project. Of this project. This is the project we did last year, but I will not talk about the project, but it's a very rough building. It's an infrastructural building, and in the inside it gets very sensual and refined. And one part of this sensuality is contributed by a ceiling system that is made out of aluminum cylinders, black on the outside, and aluminum, natural aluminum on the inside, which are assembled by a small robot that piles them, stacks them in elements 1 meter by 1 meter. So it's about 40 parts. And the only thing the robot does is to modulate the position of the cylinder by about 3 centimeters. No. And the result are elements that are serially produced out of a serial material that weighs almost nothing. You know, this is like beer cans. And all these parts are individual, and in the addition, you know, they form a very sophisticated ceiling system, you know, that again gives the horizon place with light and so on and so forth. So serial addition of identical parts, you know, to create something that is much more than the pure sum of the part you departed from. And the same logic is used in the sequential roof, with the difference that here the process includes the manipulation of one of the 3 dimensions of the element. Here you have timber slats, 5 by 10, so pretty slim parts. They are cut at the ends by a saw, but controlled by a robot. What you can control is the angle and the dimension, and then they are laid down to form large 15-meter long trusses. Again, it's a 3D printing process. And where in the brick you put glue, you know, here you put nails. And nailing is a completely industrialized process, you know. And these 2 things, cutting, bringing the right position, and nailing, are digitally controlled processes that already exist, but normally they are used for the repetitive production of panels, for example, you know. And now just by intervening at the level of the information with the same machines, but by inverting the paradigm, you can produce in a very lean way structural elements of certain dimensions that are all individual, highly complex, and that get installed in the shop, you know, with all the subsystems, and have only to be transported on site and craned at the right position and fixed with a few screws. So the complexity of organizing 50,000 slats of this size, you know, which with no identical geometries, gets simplified on the building site to the placement of 168 trusses. You know, they just have to go on the right place, and then it's fine. You know, and all this complexity that is, I said, 50,000 flats, but this means 1 million nails. You know, and given that there is no identical connection, you know, the angle is always different. The overlap area is always different, you know. So the position of the nails and the amount of nails, which depends on the connection, you know, and on the structural conditions on the connection, are always different. Here you see the result. So these are the elements. This is the model. You know, this is an overlap of different stages of this module, but the interesting part is here on the right. This is the control lines, you know, it's what you design with in the end. And all the rest, you know, down to the nailing position, to the position of the subsystem and so on, is a computational. And if you look at such a detail, you know, where you understand that it's not just two slats nailed one to each other, but there is a third one, you know, and the code tells you what the distance between two nails can be, you know. So if you nail through the first and second one, you will end up in the third one, but there you have other nails, you know. You have the extremely complex relationship between these parts, and this is something you can only solve computationally, and then you have to nail these nails. And to nail 1 million nails manually, you know, looking at the drawing, wouldn't be possible. So this building, this roof, it's 2,300 square meter in size. And this is the only plan we produced, you know. And it's not a building plan, it's more, we use it to express the elastic properties of this structure. You know, for us it's like a carpet, it's like a fabric, you know. The system, you know, exhaust and so on, they don't cut through the structure. It's a structure that makes place, creates place for this subsystem that have to be accommodated. And suddenly the drawing here is, on one side, the geometry, you know, accentuating this main primary structure, and the second one, it's like a negotiation between the vertical and the horizontal, you know. And what you perceive, if I go back to this drawings here, to this, what you perceive like almost being ornamentations, you know, are really part of the technical part of the design. And there it's where we, again, spot digital materiality, but in more general terms also think that beauty in architecture is to be found, is when these things come together in a way that is simple and meaningful, you know, and where at the end you don't have to say, wow, this is a nice... I was asked a few times why, when I show this, I could also just say, oh, it's a beautiful space, you know. But normally I explain how it's done, because I think that an understanding that is beautiful, you see, you know, because it's light, it's a resolution, it's thousands of elements and so on, but an understanding for the design process is as relevant, you know, for an appreciation of a space as the result itself. Next, this is a bit of a paradox. It's again the same logic, but here the structure in the end is not visible anymore. This project was on display at the Istituto Svizzero in spring. It's called mesh mold. It's a process where a robot, by cutting, bending, and welding rebars, produces cages. We call them meshes. Of a high geometrical complexity that can get filled with concrete. And the size of the mesh is calibrated in a way that the concrete mix does not protrude, so leave the thing. It has long tradition. Ferrocemento basically was this, you know. nothing new. What is radically new here, I think, in this video, is that you need this machine to translate geometry into this very complex physical artifact. And what is strange but also fascinating, and this was the topic at the exhibition here in spring, is that once you've filled this structure, you know, the beauty of this mesh disappears. You know, we called it the inner form. You know, so what is hidden, and what is left at the end is just the result. You know, the reminiscence, the shape, the form, the surface of the wall you created is there to testimony, you know, of this very, very complex inner structure. And here, this was just filled 2 days ago. This is the first preview image of how it looks right now. Okay. This were the building project, building technology project. So we move from practice to first steps in academia to this is a very applied technology. It is patented. Probably it has the potential, I don't know, to become a reality in building industry. Of course, there is still a long path to go. It has to become faster and so on, but the concept is visible. Now I want to move to more speculative projects. One, and also more poetic project in a certain sense. First one is called remote material deposition. The starting idea or problem is that there is all this talking about 3D printing architecture since years. Koshnevitz with his countercrafting is 15 years old, but there are a few fundamental problems with this technology. And one is that the relation between the size of the machine, the size of architecture, becomes paradox or problematic, because as long as you print an object or a car, you know, then it's easy. But if you print a house or a high-rise, you know, then having this machine that has to be bigger becomes strange. But this is the logic. So we said, why not solving this in a very simple way by just shooting the material, you know? So we separate, we say, there is no need for the machine to go exactly there, because we can, you know, ballistic technology has a long history, you know. We have learned to calculate where things land. And the little problem that we have here, that is that you have projectiles, then you know pretty well their weight and so on. With architectural projectiles, this is not so easy. But we will also apply a very old technology to solve this problem, which is feedback system, you know. In the early day of artillery, the artillery piece itself was useless if you didn't have somebody on a hill telling you if you were too long or too short, you know. And this is feedback, you know. And control has a lot. I mean, it's basically built on feedback. Here how this works. I shoot material. I estimate based on my physical calculation. Then I look at what happened and I correct, you know. And through a few loops, I will guarantee that with a high probability, my material will end up where I want it to be. So we started to produce projectiles, architectural projectiles with clay. We identified clay as being a nice material because it sticks, you know, when it impacts. We designed a robot that could direct this projectile and shoot it. And this then was the result of the process, you know. It's precise, but not too precise. It's low resolution, again, you know, what is the resolution of architecture? It's automatic, and it's very irritating, you know. And the setup was extremely simple. Again, one camera on the top, on the ceiling, this device, and the result was this, you know, an installation that speaks a language that is, I would say, at the same time familiar to us. You know, this is we can understand how it, you know, this addition, what the logic of this addition is. We can still read, you know, a lot of things about the energy that was, you know, at play when this thing collided, you know, because the deformation of these perfect cylinders in the beginning is still there and readable. And again here, for us, it's digital materiality, but in a more translated way, you know. You don't have the precision, but the precision is not something we look at, you know, in the digital. You know. Because here the material expression takes over. And the same, along the same line, you have to understand the second project. You know, it's a project where the material itself and the way it configures becomes dominant over your design intention, you know, and you don't inform the position of the single element, but you let them self-organize. Rockprint was designed for the Biennale in Chicago, the first one 2 years ago, and it builds on a principle that is called jamming in science. Jamming is a phenomenon that describes what happens when solid parts, bodies, interlock in a way where at a certain point they cannot move anymore. Just they don't have any degrees of freedom, and so it's sort of they solidify, you know. And this can happen in several ways, by giving boundary condition, by giving weight, force, and so on. And the fascinating thing is that the process is completely reversible. You know, you have this jamming transition. You know, this can go from liquid to solid, but back to liquid, you know, again. You can test this very easily at home. Cornflakes it's very depending on the shape of the particles. Of course, cornflakes are very robust, you know, jamming material. But we did it with gravel. We wanted to build with loose gravel, and we developed a process where the jamming will be guaranteed by, not by boundary condition, but by a string that is inserted in layers into the material. And this string is laid by the robot, because here the geometry is very, very, very important, you know. So this is the information, while the second part of this composite, which is the gravel, is manually added in layers. It's again a 3D printing process, you know, layer by layer, and the information comes in through the string while. And so for a few days we went up layer by layer. It's a tedious process, you know, very meditative. And you see here the pattern, of course, doesn't repeat itself. You know, the layers are all the same, but the information in the layers changes throughout the height, the section, until at a certain point you are done and you can decast the object. Here you see, this is also jamming phenomena, you know, because they were stuck. You know, now when the whole form comes away, they start to collapse. And so the final step was to bring all the material that was not tied back by the string to collapse. You know, and at the end we had this strange object. There's something in between a sculpture and a column, where the material, the weight, is placed as high as possible, because the thing works only if we have high pressure, so this slender, slim feet here have to be under compression. And if you go closer and closer, again you see this irritating materiality, and here it's irritating in several ways. I mean, this is almost 2 tons of material in the air, at the place where it should not be. And in order then to also show that this wasn't fake, so that we didn't have a steel structure in the inside, and to show how reversible this mechanism is, at the end of the exhibition on the finissage, we re-rolled the string. And by getting back this raw materials, we have a perfect division of, at the end, 1 big roll of string and 1 pile of material that goes back to its natural state, which is a slope of 33-something degrees. Here it's difficult to understand what's going on if you don't know the process. So I'm almost through. I moved to the last project. Here now we go really speculative. Aerial construction. This was both an installation and a research project we did with a friend and colleague of us, Raffaello D'Andrea, that is into dynamic control system. His object of research is drones. Drones is the ideal machine, because drone is only control, feedback and control. Mechanics is not really. So it's moving the complexity of a flying machine from mechanics to control. And what we were looking at was having a machine that could allow us, at least conceptually, to get rid of gravity and get rid of this problem the robot has, also the human has, to be fixed somewhere or to be on the ground, And the drone there has the potential, to do things that are radically new. The drone can go through something. It's like if you weave, the loom, you can shoot the loom with material through other material. This is a thing we cannot do. So we have a certain number of degrees of freedom. In the beginning, we started with very simple, a bit naive experiments, where we said, okay, let's have the drone assemble sticks. And then we found out that this is not really the best thing you can do, because it's very complex, and eventually the human is much better at doing these things, And so we got back and thought about what would a drone really want to do in construction. And then we started to work with cable structures, weaving in space. And this was a PhD work of a student of us that at the end built, and this is his final demonstrator experiment, at the end he built a bridge that humans could cross. He wanted to do it on a river in the mountains, but this was too complex, so he decided to go back into the lab. There you see how beautiful the choreography of these machines can be, They just carry material, they unroll string, But the digital controls allows them to do very complex sequences, you know. And again, let's go back to the weaving machine. The weaving machine, this is all solved mechanically, you know. Here it's just software. This then was the proof of concept. Okay. So this was the scientific research, and in parallel, and this is a thing we often do, in parallel we did an installation with the same tools, so technological and conceptual tools, but freed of all, you know, because the other things you get money, so you have to tell, oh, this would be, maybe this is the future of building, and it could be the future of building, but I think to really develop idea, it's also important sometimes to deal with ideas that have been around. You know, flying in architecture has a very long tradition. We all have these images in our in front of our eyes, and we decided to revisit this. The occasion has been an invitation by Frac Centre in Orléans to do an installation, a site-specific installation for them. And so in this collaboration with Raffaello and Andrea, we designed styrofoam blocks. It looked a bit like bricks, but were more intricate, and decided to build with them. And what we built was the model, scale 1 to 100, of a vertical city that we called Vertical Village, which was an urban project, completely speculative, inscribed in the tradition of the ideal city planning that since Renaissance has you know, every 50 years there is a specific intensity of more or less naive or utopian proposals that are always very serious, you know. They are very detailed. If you look at this project, whole books describe how these cities would be built and how people would live and how they would exchange things and how they would feel. And at the same time, it's absolutely utopian. So it's clear to the reader that they will not be built and that it's not about building them. This is not the point. The point is about speculating and talking about these things. So we applied the same technique, cultural technique. We designed this, we rendered, we acribically, you know, detailed it. We designed the modules of this gigantic, almost 600 meter high tower or wall or bent wall, however you want to call it. And at the same time, we built the model of it in real time in the exhibition. While the first part of the project is inscribed in this ideal city planning tradition, the second part is performance art, you know. It's where you do something that is potentially dangerous, you know, in between the people, and you really don't know if it will work out, you know, or if it will crash as a performance. So this piece here at the end was the addition of two parts, you know, that both for us wouldn't have made sense, you know, to design an ideal city, we don't care, you know, to do an installation with flying bricks, we don't care, but having these two parts dialoguing with, you know, asking, questioning each other, you know, about what is real and what is utopian, you know, this was the exciting part in this project. So I want to conclude just with a few statements, and more maybe also if you still have time or energy, could lead into a discussion with a few conclusions. One thing is that I believe, and probably I showed, material is becoming informed. So if we talk about new materials, we should less focus on new materials in the way we thought about them in the last 2 centuries, glass, steel, you know, so something new, but more in the new as being a new way of aggregating or constructing things. And maybe the departing material is as simple as wood, brick, or whatever, or concrete. Just as a hypothesis. Second thesis is that if we take these things seriously, we should rethink construction, or we can suddenly rethink construction. Things that for a long time have been as they are because they followed a certain logic, you know. This logic can change. The third thing is, think back to the table in the beginning, we shouldn't be scared of designing processes. Designing processes is as powerful as designing form, geometry, you know, or more powerful. And the third thing is, believe it or not, the digital in architecture has a high potential for centrality, you know. This is again for us inscribed in this digital materiality, where the digital that is supposedly called rational, scientific, exact, you know, suddenly produces something like this. And my final message or conclusion is that I think that we should really stop thinking in dichotomies, you know, where one thing excludes the other, and start to understand the digital as just one component of our reality, you know, that does not exclude other realities, you know. Nobody would program certain things. I never thought about not sketching stuff. If I think that sketching is more efficient, I sketch things, just because I was trained to do so. But I would never sketch things that are unsketchable, you know. So it's about recognizing the right tool at the right moment. And this, by doing this, we can really start to address this topic. I often think of the digital in architecture as being sort of the elephant in the room, you know. Everybody knows that it's there, but nobody really wants to talk about it, you know. We all try to, you know, avoid it because it's can be scary, you know, can question a lot of things, but at the same time it has a huge potential for the profession, and not just in terms of productivity, you know. It's not about the survival of our profession. It's also about the survival of our profession, but first of all, I think it's about deciding if our profession will be an interesting one, a creative one in the future, or not. You know, and this is at stake now, and it's up to us to answer, you know, because maybe it's a bit negative, but I really believe nobody will wait for us, you know, in any way, you know, and history has proved this. We have been marginalized from construction, you know, because we basically gave up a lot of competences. So in the future will be about getting back these competences, you know, and acting proactively, you know. Thank you very much for listening. And